Hello, my name is Christopher Ramos. This is my Nano-manufacturing course assignment, 3D NAND flash schemes. In this instruction module, we'll be looking at 3D NAND flash architectures that are appearing on the market. At Toshiba, Dr. Fujio Masuoka in the 1980s came up with the idea of NAND flash. To get the basics of this idea, we'll start by looking at a planar NAND array. And so what you notice about the planar NAND array is you have the select transistors on either side of a whole string of word lines. And you can think of all these word lines as cars parked in a parking lot. They're taking up space. Everybody wants to move to smaller and smaller areas. And if real estate is expensive, you really want to stack these things on top of each other. And so how do we do that with 3D NAND? What we can do, we can take the NAND string that we had. So we have our select gates here, and each one of the word lines here. So we've just folded it over, and then what we want to do is stand it up. What does this gain us? Well, for a 16-cell vertical string, that will effectively shrink its production process size by 1/4. And going back to the parking lot analogy, we can see that to save square area, people go vertical, and that's what's happened with 3D NAND. This allows engineers to continue to produce functionality at an equivalent technology node. The storage capability of 3D NAND is what would be equivalent to, say, the 10 nanometer node here without actually having to produce at the 10 nanometer node. So we can be up here at, say, 30 or 40 nanometers and still get performance as though we were operating the equivalent technology node of 10 nanometers, and that's what 3D NAND has really brought to the market. We see the evolution of the floating gate. So again, this is back in 1971. This goes to a charge trap flash device where now you have a electron trapping layer insulated from your gate by high K dielectric as your insulator, and then your control gate material. Well, this has been taken and put into 3 dimensions by putting them in cylinders. So again, you have your channel in the middle, your charge layer, an insulator, and your control gate, and then that's wrapped around into a cylinder, and these cylinders are then stacked to make your 3D vertical NAND gate. So there are basically 5 types of NAND architectures. So we have the Bics, the PBics or pipe Bics, TCAT, VSAT, and the vertical gate or VG. And I'll talk about what each one of these means as we go through. First, we'll start with Bics, which is the bit cost scalable design. This is Toshiba's design, and we start by laying down a CMOS logic layer, and on top of that we'll put silicon dioxide as an insulator, and then a polysilicon layer is grown on top of that. And this can be considered to be the first word line of this stack. And then we keep stacking and stacking. So we're depositing layers until we decide we have enough. And what we want to do then is etch an array of cylindrical holes through all the way down to the base layer. So our next step is to etch, and we go ahead and do that. And that goes all the way down to the silica substrate. So a process note that these are long trenches and they're difficult to manufacture. But only one mask is needed to produce this entire array of holes, and that brings the litho cost down. So we have a pro and a con right there. So the floating gate channel is next, and that's to deposit a silicon dioxide on the walls of the hole, and that makes the dielectric. The next step is to have silicon nitride trap deposited on the wall, and that acts as the floating gate. Next, a layer of oxide is then deposited onto the silicon nitride to form the tunnel dielectric. Now note, this is 3 consecutive tubes that we have in this structure. So finally, the central hole is filled with polysilicon, and that helps produce one branch of the U-shaped structure of this Bics design. So in this more polished graphic, you see the U-shape that I'm talking about. We were looking at one cell of that U-shape, and we see that the long slits that are etched along this plane to help separate the tubes. So there's another there, another there, another there. So if you imagine that in 3 dimensions, this these long slits have to be etched out to separate each one of these U-shaped structures. So scalability in this design is going to be determined by the minimum packing of these tubes. How small can you make those tubes? And today that's not something that's known. We might be able to scale these much further than we have right now, but like I say, that's for the future to be determined. So another nice picture is to look at these in real life. What do they look like? So this is a scanning electron micrograph of one of the Bics designs, where you have the upper select gates, you have all the control gates in the middle, and the gates at the bottom. You also see how they're wired in, so each one has a staircase feature attached to it, and the data lines are attached to it through these wires that come into the stair steps. And we'll talk about the manufacture of that in a moment. And so if you were able to look at it in 3 dimensions, this is what the chip would look like if it were blown up. This is what it looks like just looking at it with your naked eye. And the next technology we'll talk about is TCAT, the Terabit cell array transistor. This was developed by Samsung and Hynix, and they use what's called a tantalum alumina nitride oxide system, and this is the Tano system, and it forms the basis of the TCAT array transistor. In this construction, again, your CMOS logic is laid down at the bottom, and silicon nitride is used instead of the polysilica as a substrate, and you keep building this up and building this up. If you think about it, you have a stack of insulators that are stacked up, and we're going to see why we're using the nitride in this case. The next step is the same as Bics, where you etch a hole down in through your stack, and here the hole is lined with polysilicon. We're not using the nitride oxide layers like in Bics, so this is different. We put the polysilicon on the wall. The silicon dioxide is then used to fill the hole. This is supposed to give better subthreshold characteristics than a solid core of polysilicon. And now actually we go on to make the gate. So the next step in making the gate is to etch slits along each side of the column like in Bics. So we have our central column, we etch the slits in, and then next the nitride layer is etched away selectively. And what that does is it leaves the central column with the fins on it. So that's our silicon dioxide tunnel oxide is deposited, and then a silicon nitride trap is added to that. That's the charge trap. And then alumina, the high K dielectric, is going to be added to fill the gaps. And then tantalum nitride is then used to fill in these holes. Now, once the tantalum nitride is in, it will be etched out of the slit so that it's removed, and the alumina is removed from the surfaces of the fins. So we etch the tantalum and the high K, and what we're left is a central column that is now a string of vertical NAND Tanos transistors. So we notice that in TCAT we built the gate last, whereas in Bics we built the gate first. Both of these are gate all-around structures, and a gate all-around structure is nice because it provides a lot more surface area to couple the control gate to the charge trap. And we know that a problem with planar scaling is that the coupling capacitance with the control gate and the rest of the transistor decreases as the transistor gets smaller. So again, the TCAT holes might be able to be made smaller because they only have the material of the polysilicon on the side and a core filled with the oxide. Whereas the Bics, you have to deposit 3 concentric cylinders inside each one of the Bics holes. So here TCAT may have a production advantage. If we look at this slide, we see a nice picture of what these actually look like, and we compare that to the cartoon on the right. Again, you see the stack of gates. It's a gate last, gate all around, and you see that these are relatively large size. What are some of the manufacturing problems with connecting the gates? It can be difficult because some of these gates, when they're litho etched to make the stair steps can be uneven. You may have wiggling on this face, you may have slanting of the gates as they come in, and what happens is that makes it very difficult to land the connectors in appropriately. So this one's missing a step, that one's missing a step. Applied Solutions is a company that has plasma etching devices that they've employed to really straighten this up to get equal step spacing and to give you much cleaner edges on your stair steps, making it easier to land the connections as you go forward. Also, you're looking at very high aspect ratios of these trenches. In some cases, they're 80:1. And what can happen when you're producing these is that as you etch those, the hole can walk off, it can bow, you can have bending, so this whole thing bends this way. And you also see that some of these circles in the top mask, so the top of these holes, you can see that they're not circular. Well, if you use the Applied Solutions plasma etching, you see that you get much straighter walls and less bending, so there's no bending here, and you have these are much more circular in the production. So Applied Materials is one company that has developed these plasma etching techniques to improve reliability and reproducibility. VSAT is vertical stacked array transistor, and this is a device that was designed by Device Research Laboratory from the University of California at Los Angeles. This is an array transistor design that should alleviate some of the issues with the stair steps by not integrating the select gates into the stack like in Bics. So here there are no select gates. These are all control gates in the stack. Now what that has the advantage of doing is that now you have a more monolithic construction. You've eliminated the staircase, so instead of having each contact come in a staircase, you can have the contacts come in on a plane, and this is much easier to land the contacts on a plane than it is on a staircase. Also, you've removed each litho etch step that you have to do to produce the staircase, and so you've come up with a design that may have lower production costs than the Bics design. Hynix has proposed a three-dimensional floating gate design that we see here, and Macronix has proposed a vertical gate design with what they call a twisted bit line, which allows for split page construction, and it winds up reducing the word line and the bit line half pitches to about 37.5 nanometers along this dimension along the word lines, and 75 nanometer half pitch along the bit line direction. This design again has done away with the staircase that you see in Bics. These are some visualizations from Toshiba looking at the stacked array in cross-section just so you can get an idea of what some of these things look like. Here we're looking along the word line. Here we have each gate stack. You can see each one of these sets here is a gate. You can also see the walk-off of some of these trenches that have been dug. Again, the plasma etching is supposed to eliminate some of that. And finally here you see each of the NAND chips themselves being stacked and wired out in the stair-step arrangement so you can contact to the outside circuit. A summary of the gate. So we have the pipe Bics, which runs the current in a U-shape, so around here. So it's a gate first design. We build the gate first, the current takes a U-turn, gate all around. The TCAT is a gate last design. Again, the gate is constructed last, the current flows vertically, and it's a gate all around design. And with the vertical stack, you have the current making a multi-turn, and it's a planar array. And all of these are working right now at the 50 nanometer node. Now, the vertical gate is a gate last construction. The current flows horizontal, and it's a double gate design. And this has the potential to work the 2x nanometer node, and that means that this is probably one of the most promising of the 3D NAND structures to come out of the production lines in the industry. That's a really nice picture of what this looks like close up. That's a Bics construction. The references, places where I got information and images in this talk are listed here. And once again, I thank you for joining me and spending your time with me to look at the 3D NAND flash.